Thanks, everyone. Thanks for that introduction. I hope you're all having a good CraftConf so far. My name is Sarah. I work in the blockchain industry. I'm currently contributing to a project called Circles UBI, which is a universal basic income pilot on the Ethereum blockchain. So I'm also one of the co-organizers of a conference called R Networks, which is about all aspects of the peer-to-peer and distributed web. The next version of it will be taking place in September in Toronto. Our theme this year is regarding infrastructure, and our CFP is going to be going live on our website any day now. So the structure of this talk is going to be sort of two parts. The first one is going to be an overview of the peer-to-peer web. We're going to do little vignettes of some of the popular emerging protocols. And then we're going to do a section of, if you were interested in building for this peer-to-peer web, what might you use? So the first part, what is the peer-to-peer web? But before we answer this question, let's talk about what is the centralized web. This is a map of the internet. It shows the backbone cables that connect large geographic areas. But this is another way we might map the internet. And this is in terms of traffic and ownership. So the size of these circles is determined by traffic. So you can see that massive amounts of internet traffic are funneled through just a few portals. And the disproportionate size of them is actually greater than this map shows because, Google and YouTube are owned by the same company. So yes, we have a galaxy, but also just a few main players act as gatekeepers to our browsing control flow. And this, by the way, is the portion we were just zoomed in on. So the centralized web has given us a lot. I'm sure many of you work on it. I have too. But it comes with some problems. And this is honestly a fairly simplified set of arguments. I also do a more than half-hour-long talk about centralization versus decentralization, kind of why decentralize. And it's complicated. I think the most important conclusion to come away with is that both of these things offer trade-offs. It's important to understand what those trade-offs are. So the centralized web can be unresilient. Something like 40% of the internet runs on AWS. So in the case of an outage, we can see massive amounts of it go offline. There have also been examples where a severed deep-sea cable, in an extreme case, leaves an entire country without internet for several days. With this concentrated power means concentrated ability to restrict access to content. So we've seen government shutdowns of specific websites, and in an extreme case, an entire country lose internet for 280 days in the case of Cameroon last year. And finally, users have no control or visibility into what happens to their data. So this is how the centralized internet works in its most simplified state. A client makes requests and a server responds to them. And yes, this server is probably some constellation and/or clusterfuck of microservices. But this is a simple case. In the peer-to-peer web, that goes away. These nodes, which are all equal in some hierarchy, take on roles, but in turn, they are both requesting and responding to requests. So it's important to know that this peer-to-peer web movement I'm talking about, and maybe we're experiencing a renaissance right now of peer-to-peer, is hitting every layer of the network stack. So we're seeing renewed interest in community mesh nets, distributed domain names like the Ethereum name service or something called Handshake. There's a data and protocol layer, things like IPFS, Ethereum, and most blockchains. Older protocols like BitTorrent would fit in here as well. There's an application layer, so things like Mastodon, which you may know as the federated Twitter. Most dApps. DApp is the collective noun for a blockchain application. And there's also this governance layer, which is the human layer that governs technology. And these things like Lumio or DAOs, decentralized autonomous organizations, are concerned with how we prevent the centralization of power. For the purposes of this talk, we're going to be focusing on this data and protocol layer. And of course, decentralization has many problems too, most of which we don't have time to go into in great depth in this talk, but some of them are the tooling is immature. So a lot of these projects are new. They implement only a small subset of their planned features. The plus side of this, of course, is that there's lots of low-hanging fruit, a lot of simple projects that the community needs that haven't been built yet. We have unsolved problems of scalability. So this is an emerging area of distributed systems research. How do we make protocols like this scale to meet the traffic of the centralized web? And then finally, the Spider-Man dilemma, with a high level of user control means a high level of user responsibility. I've seen the entire question of whether the peer-to-peer web will be adopted en masse condensed down to, will the average user ever be able to learn to manage a private key? So we also have a lot of UX problems. Let's move into some vignettes of popular peer-to-peer protocols. This is probably the best known one, which I'm sure many of you have used. It's BitTorrent, and we use it for file sharing. This is where you get all the best Linux distros. So it has multiple clients. BitTorrent is a protocol. Two of the most popular ones are BitTorrent and microTorrent. This is a screenshot from microTorrent. So this person is downloading multiple files. And there's a concept of seeding and leeching. So seeding is making requests to, seeding is providing data to the network, and leeching is requesting data from the network. In terms of structure, one of the things BitTorrent innovated over the many earlier file sharing protocols is that you could download multiple pieces of a file simultaneously. There were a lot of interesting attempts to enforce good behavior on the network, so early reputation systems, trying to make sure you're seeding a certain amount of data in order to be leeching at a good speed. Architecturally, it did still do content discovery with a centralized tracker. So when we see governments try to take down the BitTorrent network, which they love to do, it is these centralized trackers they usually come after. A protocol you might not have heard of, newer, is Scuttlebutt. Scuttlebutt is an offline-first social network. And what do I mean when I say offline first? Scuttlebutt was actually created by some of the early people involved, lived on boats. And living on a boat, you have very sporadic Wi-Fi connection. So they wanted something that they could write posts, share with their friends, and use and browse with very sporadic internet. And Scuttlebutt, the term, comes from sailing slang as well. So it says here Scuttlebutt is a social network. Really, that's an abstraction. It's a way of posting messages. Similar to BitTorrent, Scuttlebutt is a protocol with many clients. So this is the most popular one. It's called Patchwork. It runs on desktop. There's also an Android client called Manyverse that came out recently. When you're using Scuttlebutt, you'll see a variety of familiar aspects you would encounter on any social media network, like a friends list, space for posts. But you'll notice here that my profile is identified by my public key. So this is how posts are verified as being from any given user. And the internal structure of posts is very similar to a blockchain or an append-only linked list of all the messages I've sent. And indeed, thinking of Scuttlebutt as a series of individual blockchains, so I have my list, you have your list, which are synced across a social media network or social graph, is a very good mental model. There's also, so because content, new posts, is only available when someone is seeding them, there's another role in the system called pubs. And pubs are just like ordinary users. You can see here that my Scuttlebutt is connected to a couple posts, pubs. And these are usually run on a server or a computer that can be counted on to stay online, like you might be familiar with a seed box from early BitTorrent days. And pubs issue invite codes. You can get an invite code any number of ways by knowing the owner of the pub. Some of them just give them out. And if you have one, the pub will follow you back. So these are used to build out the SSB or Scuttlebutt social graph. And the reason we want to build out the social graph is because this is how data travels on the network. So this network is offline first, which means you're storing some portion of the network's data on your computer. But what you store is relative to your place in the network. So you sync and store posts made by your friends of friends, and several hops out. The amount of specific hops is configurable based on your client. but what you see and what you store is relative to your place in the network. So a kind of interesting thing that will happen when you're browsing Scuttlebutt is sometimes you'll see a thread of posts and only some of the messages will be readable to you because the other ones are posted by people who are outside of your social graph. They're too far away. So Scuttlebutt is an example of a gossip protocol, and that's what the word scuttlebutt means in pirate slang. And what it means here is that posts are passed through the network. So you can see here that Bob, Carla, and Alice are all connected to a pub. Dan is not connected directly to Alice, but because messages are passed transitively through the social graph, Dan can still read Alice's posts. She's not so far out, and her messages will travel to him. Another popular protocol, and I will confess the one I know the least about personally, is DAT. I did try it out for the purposes of this talk. It was created by the scientific community for sharing data. A quote from the DAT site describes it as taking the best parts of Git, BitTorrent, and Dropbox. And it's used mostly for publishing and hosting. Similar to the other protocols we've looked at, DAT is connected to with a client or browser. In this case, literally a browser called Beaker. So you wouldn't say that DAT is offline first because it doesn't by default make copies of what you look at, but it does work well over local networks that might not be connected to the broader internet. When it is connected to the broader internet, it uses a centralized discovery server analogous to BitTorrent Tracker to help discover peers. This is another peer-to-peer social media network. This one runs on DAT. It's called Fritter. It might look a lot like something you're familiar with called Twitter. And you can really see the similarities to Git here, because when you click up here, there's a button to make editable copy. And also note the protocol identifier. So Beaker browser looks at DAT links. So when you click to make editable copy, this site will get put in your library, which looks a lot like GitHub. It has familiar features like a dat.ignore file, like a gitignore. And you can also see the version history. So DAT comes with built-in version history, and it's tracking changes to this folder. So unlike Scuttlebutt, DAT has no pubs. So data that you request isn't persisted locally or shared unless you explicitly choose to seed it. But there is a service called Hashbase that you can use to keep your data available when your computer is offline. DAT also has a command line interface, which is, again, very similar to Git. It has commands like dat create, which creates a DAT, and DAT is the name for a folder or blob of data that you are sharing with the DAT protocol. So dat share would be maybe analogous to Git push, and we also have dat clone. When you're thinking about DAT versus Scuttlebutt, a distinction that I think is helpful and interesting, made first, I think, by Andre Stelz, who is the creator of Manyverse, the Android Scuttlebutt client. He describes them as DAT being good for finding any the content you choose from whoever has it available, and Scuttlebutt for picking the people you're interested in content from, but whatever content they post. So chosen content, any peers, versus chosen peers, any content. And BitTorrent would be another example of chosen content, any peers. So also like Scuttlebutt, DAT uses public and private keys, but just to make the chosen content distinction clear, DAT uses the keys to identify the specific DAT, not the user who created it. So we can't forget blockchains. This talk probably wouldn't be complete without them. They're the most buzzwordy peer-to-peer protocol today and my professional specialty. We can think of them as a distributed ledger or state machine, depending on the blockchain we're talking about. And there are some very unique concepts in blockchains that are different from the other protocols we're going to talk about today. One of them is they have global consensus. So very unlike Scuttlebutt, where what you see in the network is relative to your position in it, all of the blockchain network agrees on the state of the chain. And if we were to map a blockchain onto more computer science terms, we would call it an append-only linked list. The reason we have these features, which are different from these other protocols, is the very specific use case of money as a primitive. So we need to agree on who has what money, thus global consensus. We also need to know what order transactions happened in. So thus we have append-only. And blockchains also have mining, which you probably know about. It's the creation and propagation of the network that being financially incentivized. And the users who are interacting with it are paying transaction fees. So transaction is, again, a word from finance, from a money use case. A good mental model for a transaction is a message of signed intent. Usually a transaction is sending some type of cryptocurrency, so Alice sends a Bitcoin to Bob. We identify that transaction by its hash, and we put it in a block. But this message could be some other intent. It could be, asking us to perform some piece of arbitrary computation on a blockchain like Ethereum. It could do anything. And we link these blocks together in a chain. So we take the hash of one block, we put it in the next block, we hash that, we put it in the block following, and it makes it easy to detect when any of this data has been tampered with. There's also an important feature called a nonce, or number only used once, and this is part of mining. So what the miners are doing is guessing these nonces, trying to find one that meets the criteria of the network you're on. Another protocol is IPFS. IPFS stands for InterPlanetary File System. This is made by Protocol Labs. It's a content addressable file store. So it's used as the file storage component of a lot of peer-to-peer applications, including many blockchain apps. When you're running an IPFS node, you can look at this in your browser. And it'll give you a bunch of information like your peer ID, your location, and your public key. When I start up a node, I almost immediately connect to over 100 peers. And it's kind of cool. There's this way that you can see them all over the world. So it's a very popular network. What does it mean to say something is content addressable or a content addressable file store? Well, most of the internet is location addressable. So we know the IP address of the content we're looking for, but not necessarily anything about that content. And one of the problems with location addressability is we might travel farther than we need to find what we want. It also makes no guarantees that that content is actually what we expected it to be. So maybe an analogy from cryptography would be receiving a message with no authentication code. We don't know that it was what was sent. In location addressing, we're usually identifying a blob of data by its hash. IPFS uses Merkle trees, which takes a variety of leaf nodes, builds them up in a tree to arrive at a root hash for the entire data blob. Merkle trees have some nice properties. One of them is that we can generate Merkle proofs, which will allow us to prove that a certain piece of data is part of the root hash without revealing all of the leaf nodes. They also allow us to trivially check if any of the leaf nodes have been changed or the tree has been tampered with in any way. This is similar to a blockchain, except it's not linear. Here are some examples of IPFS links with their root hash. So let's see if my internet is working. So this is the videos from our networks. We do our live stream over IPFS, and we host all the videos from our conference here. So this is the root hash of the entire blob of all of the videos. And this one, there you go, you can see it. This one is kind of interesting too. This is the IPFS site for the content addressable storage Wikipedia page. And I think this is kind of interesting. It's hard to see. So this root hash actually is the root hash for Wikipedia itself. So there's something kind of sublime about that to me, like the root hash for all of Wikipedia. There was a project a couple years ago to put Wikipedia on IPFS when access to Wikipedia was blocked in Turkey. So it's a kind of cool project and a good example use case, actually. So we've done vignettes of a couple protocols. What are some common elements? One, they all use cryptographic keys for identity. They have a protocol, which is a base layer that many clients access. On these networks, all of the nodes are storing some or all of the data at various points, and they are in turn acting as client and server. And they all have common problems too. So this is a graph of the network use of an IPFS node. It says bandwidth usage of our experimental IPFS node. In this test, the node was not used to browse or download any IPFS content. However, over a period of 8 hours, our node downloaded and uploaded 5 gigs of data. So that's significant, a lot of network traffic. Maybe not everyone wants to run this on their personal laptop. Also, privacy is a weakness of a lot of these protocols. So on blockchains, for example, the best you have is pseudonymity. All transactions are visible. On DAT, even without knowing the specific public key of any actual DATs, from observing the network traffic, you can tell how many are popular, their approximate sizes, and which IP addresses are interested in them. Most of these protocols in themselves contain no attempt to mask IP address. So there are privacy trade-offs that need to be understood when you're using them. Let's look at the second part of the talk, which is if these are interesting to you and you wanted to try them out, not by using one of these protocols, but by building one, how might you get started? A great way to do this would be with libp2p. So libp2p is a collection of peer-to-peer protocols, really an application framework for building peer-to-peer protocols. The goal to make this sort of generalized toolkit. It was originally the networking framework for IPFS, but it was extracted and is now its own first-class project, also being developed by Protocol Labs. There are implementations in Golang, Node.js, and Rust, and there are implementations underway in a bunch of other languages like Python and Haskell and Java. So on this graph, the colors represent sort of different aspects or components of the peer-to-peer application, and the names in the hexagrams are the different modules. So we have transport. This is the protocol that goes over the wire. Discovery, how we find peers. Peer and content routing, so how we choose paths through the network. And NAT traversal, which is how we maintain connection over a gateway. So an example would be a home router, which is an intermediary between devices on the local network and the big bad outside internet. So there's not a perfect overlap here between the modules and the roles. So you'll see, for example, the Kademlia DHT or distributed hash table. It can do peer discovery, but it can also do peer and content routing. Same with multicast DNS. The goal here is to allow you to upgrade or swap out any of these modules without changing the bulk of your protocol. So say there was a security vulnerability found in MDNS, and it was patched, so you want to upgrade that, but you don't want to change or swap out the rest of your peer-to-peer stack. libp2p would allow that. One of the main concepts of libp2p is a multi-address. So you're probably used to the first kind of address. This is a location-based address with an IP and a port. But this isn't very specific. It doesn't tell us anything about how to connect. Usually we end up just inferring that based on the port number. And so here are some examples of multi-addresses. Multi-address is a proposal also being worked on by Protocol Labs. My friend Lars is writing it up, and they're hoping to put it in front of the IETF. So you see first the type of address, IPv4, IPv6, or DNS, then the address itself, and then it tells you which protocol it's looking for connections on, and then the port. And if you're running another protocol on top, for example, WebSocket over TCP, you can append that to the path as well. So you get this Unix-like file path. Here are the various addresses of my local IPFS node in multi-address format. So you have a bunch of different types of addresses, home, local. They're all running over port 4001. They're all running IPFS, and they all have the same node ID. One of the concepts of IPFS is a bundle. So when you're building an application, you're likely not interacting with libp2p directly. Instead, you're using a bundle possibly created by someone else. But you can create your own bundle, too. And this is where you pull in the modules we looked at on the earlier slide. So this is probably the simplest possible libp2p bundle, which defines only a transport layer of TCP. This is a slightly more complicated, but still very simple libp2p bundle from a little application I put together to explore more. So this one adds stream multiplexing, which is going to let our peers discover what protocol to communicate on amongst themselves over the wire. We've added encryption, so SecIO, the messages we're sending on our protocol are going to be encrypted. And we're going to use multicast DNS for peer discovery, which will work well over a local network. This lets us use a DNS-like interface when you don't actually have a DNS server. So now we are going to do a quick demo of something with this bundle. So let's call this one peer 1. And let's call this one peer 2. And you can see that they've connected. Let's open up one more. Let's just call this one listener. All right, so our nodes have all found each other. Let's try sending a message. I hope you can read my terminal font. So you'll see that both of these nodes were able to send and receive messages. And this listener node can also see the entire conversation. It could send messages too if we wanted to. So let's look at the code that went into making that, because it's shockingly simple. We have a create node function. This instantiates a peer info object, which is a libp2p built-in. We give it a multi-address. And then we call start on it. Now we have a node. This is the run function that does most of the work. So you see here the multi-address again. We're going to listen to all IPs on the local machine and also with a wildcard port. We're going to listen for peer connect events. And when we get a peer, we're going to subscribe to a pub sub called yelling. We're also going to listen on standard in for incoming data. And when we receive it, we're going to publish it, yelling, on that same pub sub down here. So this is really all that went into that. It's a couple hundred lines of code. It's very easy. But I find it also very inspiring to start to see how these pieces come together and imagine how you might extend from here. For example, you could give these nodes a local file store. You could start to look at encrypting these messages so that only some nodes receive them. So you can start to think about how you might build from there. So this is what we've talked about today. We've seen an example of an MVP peer-to-peer application, a quick tour of the library I used to make it. We've talked through vignettes of some of the popular emerging protocols like IPFS, blockchains, DAT, Scuttlebutt, with analogies to the BitTorrent network, which many of you probably know. And in general, we talked a little bit about what the peer-to-peer web is and why you might be interested in finding out more about it. So thanks. This is my contact info if you'd like to stay in touch. This is the repo for this code snippet that I showed you. If you're interested, I'll make it public. And if you are very, very motivated, this is my Scuttlebutt public key. If you would like to look me up on there, you can type that out. So thanks.
Thank you so much for the presentation. We have some questions at Slido, so it would be great if you could answer those.
The first one, yes, this is true. It does need to be updated when Wikipedia is updated. It needs like an additional layer to handle that, which in turn makes you think that it might have been more interesting in some ways to undertake that project on DAT, which comes with built-in versioning. But the people who did it did use IPFS, so yes, you were right. Second, no. Spider is not the only web developer who enjoys finding bugs. And what operating system do I have on my laptop? I have Xubuntu.
Okay, great. Thank you so much. We would like to give you a little gift. As an artist, I think you would appreciate this. It's a small notebook with also a portrait of you. And
Cute. Thank you.
Okay, so thank you so much.